Okay, so we're going to get started soon. I just wanted to let everybody know the order of the groups before we actually start, just so you know when you're going to be. So we're going to start off with Covfefe Kafka, and then we're going to do Hack Overflow, then the Scope Creeps. Hopefully the scope didn't creep too much. The Injectors, Streamers, Go Jet Yourself, Downtimers, Every Day on Poland, and Flow Symmetry. So that's going to be the order, just so you know. So after we go through the prototype form, I'll put up a link to a poll, and then each person in this room can go on vote. Hopefully not for yourself. It's kind of cheating, but you can't really control that.
Like midnight or something. And basically after we
Doesn't.
Okay. Disconnected? Yeah. Yeah. Let's get them to plug in. Can you send it to me quickly?
Yes.
So this microphone will work. Okay. Okay. Where? Yeah. Send it to me. Send. Send.
All right, let's kick off this prototype form. So I kind of went over the order before each group, we'll kind of call them out, and then we can go from there. So first we have Kafifi Kafka. So take it away. And a reminder, try to keep it in the 3-minute time range.
Yeah. Right. This works, right? Okay. All right. So slides at the last minute, but let this load up. Yeah. All right. So what we essentially wanted to do was change the controller code a little bit to incorporate a message bus in between what the actual business logic is, that is the intent of what you want to do with the peering router, and how the components underneath sort of behave with it. So what we've really implemented is there's a Kafka bus in the middle, and we have sort of a combination of action as well as threshold logic in the intent, which is a simple YAML specification. And what we essentially do is send telemetry data from the router into a collector that pushes it into the monitor data topic on Kafka, which is then processed by the telemetry processor, including the business logic coming in, which determines the threshold on which it should process it. And once it's done that, the event is generated along with the business logic for the action that needs to be taken either into a vendor API or into GoBGP to create overriding routes. One of the reasons we wanted to do that was some of the vendor API modules that you can implement this way are completely disjoint from the controller logic because they're separated out by the message bus. So if you implement it this way, you now have the capabilities of potentially doing not only route updates, but any overriding LSPs that you might want to set up purely based on the API module that you want to bring in. So that helps us bring more types of logic in. And maintaining the initial logic that you had with the controller using BGP, we effectively get GoBGP in there. We didn't get time to connect to the GoBGP API at the end, but effectively the business logic would be transformed into a GoBGP API call to do exactly what the controller was doing initially. So in this case, we've just incorporated the logic and isolated through the message bus. In the rest of the setup, we just have two Quagga instances running eBGP to the router 1, and they're pushing certain routes into it. What we want to be able to show in the demo is when all the conditions are correct and the threshold is exceeded, your routes that are incorporated in router 1 should be the application routes, which override the eBGP route because the application route has an admin distance of 15, whereas the eBGP route is admin distance 20. So we've got a few pieces running. Let's hope this works. Right. Running. Running. All right, so you don't actually see what he is running, but effectively he's getting all the telemetry data and is processing and creating the events that need to be processed. So when I run my client here, it's going to poll on both the business logic as well as the event data. As you can see, I'm getting event data is equal to 1, which means that at this point, my threshold is already exceeded, so I need to actually create an override route. As you can see, of course, we need to make this a lot cleaner. As of right now, it's either creating an update message or an add message. Here we're using the ISXR service layer API, but you could use whatever vendor API. So whether you want to bring in Juniper's Jet API module in, it'll work the same way. And what happens on the router is, so you see all of these are BGP routes that were initially published in. And here I have an application route that was pushed in by the controller to override it. So we're using 10 now. So 10 is the admin distance that we're pushing in through the business logic coming up from top, right? So, and of course, if we change the threshold to a higher value, such that it doesn't meet these conditions, then the application route will be pulled out and you'll be back to using the original BGP route, which was using 10.1.1.10 as the next hop instead of 10.1.2.10. So we're overriding it this way. I think that pretty much covers it. All right.
Thank you.
Thank you.
So next up we have Hack Overflow. Where are you? And when they're complete, we will have the scope creeps.
Good evening, all. Thank you for this huge opportunity. We are graduate students from the University of Colorado Boulder. Bebop. So we've been working on a multi-homing scenario in BGP. So basically what BGP is mostly used for, you need to have redundancy if you're connecting to multiple ISPs. So that has been we've been working on. So rather than doing a simple manual scenario where you connect to one ISP and then you decide to go to another ISP, we have used a scenario where you continuously poll both the ISPs and decide, depending on the latency, to either take this ISP or take the other ISP. So this is a draft model of what we made. We were not able to make a formal PPT model because we didn't have sufficient time for that. So what we did was basically, you can see three ISPs over there. That's ISP1, ISP2, and ISP3. And we are using RIU instance or ODL instance as controllers. And then we are using Mininet in order to simulate the topology. And the Mininet would have the host and the OVS switches on them. And you can see that topology as a diagram over there, considering RIU as a controller, virtual switch, and then the host. The main aim of this particular model is to use a Python script in order to poll either ISP1 link or the ISP2 link in order to see which is having better preference, to select based on the latency, to see the average RTT, and to see the packet loss. When the packet loss for either of the link is low, it will select that particular link. So in this case, the RIU is the first BGP is connecting using external BGP to both the ISP2 and ISP3 and using internal BGP for connecting the Mininet host. And the script and the remaining process would be explained by my team member.
Thank you. Hello. So, some might be wondering that why we are just reinventing the wheel and doing the same thing. But the objective here was to actually use actual SDN. So it's not just NFV, like people use NFV in their topology and think it's SDN. So this is the actual SDN where we use the OpenFlow protocol. And the RIU controller actually runs good with Python. So here what we are doing is that what the script will do, it will poll the various ISPs and so we might have a local preference for a particular route. In spite of congestion in that path, the preference still remains the same. So what the Python script will do is that it will check the latency and other parameters and accordingly change the local preference dynamically. Also, for the we have operations team in the company, like the engineering does main stuff and operations has to handle it, monitor it. So there will also be a web UI which will continuously display the topology, including the congestion, which route is being preferred. Also, we have not ignored security here. So what the Quagga router will do is that it will, currently in the model, it mirrors the packets to another system where a snort system is there, which is having certain rules. So any unrecognized peers which are trying to connect on the port 179, they will automatically blocked or by ACLs or something. So I think that is what we are trying to do. Yeah, that's it. We are not trying for any live demos because now it sometimes works, sometimes it doesn't work. So yeah, that's it. Thank you.
We've executed this, and like we could see the best path from one ISP and then the local path, because both the ISPs are going to the same host. So 56.0 is the address of the local host. So here we have two ISPs. The first ISP path is still getting the route, but it's not been preferred as indicated with the arrow. And the next one is the local path, which has been preferred. For example, if the latency of the path decreases, it will automatically shift to the other one. Thank you.
All right, next we have the scope creeps, and then after them will be the injectors. So please be ready.
Hello, my name is John O'Brien. I'm here to represent the scope creeps. Insert product name here. So the idea we had is that this is the image you should have in your head is essentially of unequal cost multipath. The idea is we have a bunch of different network paths to choose from. We have link speeds, link states, utilization, but we also have things that change dynamically. Think about wireless backhaul networks where modulations change, link conditions change. So we actually want to be able to feed that information back into our routing protocol to make better routing decisions and use more of the available capacity in the network. Here are some of the tools that we played with today. Network X, Celery Task Queue, Bootstrap, Flask, Grafana, and InfluxDB. In our demo, we have maybe 2/3 of these actually working and doing something. Very high level overview of the sort of data flow that we envisioned. Basically, from the network, we have various ways to collect topology information and some of the more conventional kinds of metrics showing capacity, as well as what we're calling pipe mapping here, which is taking some of those other more sophisticated measurements or measurements of the link capacity, the real effective link capacity, ingesting that, going and shoving that into a database. We envisioned using Influx. We have a demo that's working with static files. Basically, this is the fake news part of this this demo. And then sort of two pieces on the back end. There's an analysis piece based on Network X that pulls the topology and the link capacities out of the database, computes maximum flows end-to-end for networks of interest, and then makes that available for a Flask UI to sort of show in a dashboard form. The concept that we had that we didn't get to poke at it at all was taking the results of that analysis and feeding it into a routing protocol of some sort. Here are some examples that we thought we might use. Essentially, the requirement on that routing protocol is you've got to be able to say that at a particular point for a next hop, I want to weight the traffic, so I have some portion of the traffic taking this outbound link and some different portion of the traffic taking this other outbound link. And that would be the full end-to-end feedback loop for the control. This uses the maximum network flow problem, and we were able to leverage algorithms that the Network X Python library provides for us. This is the sort of sketch of what the dashboard might look like, where for the networks of interest or the endpoints, we say from here to there, is there enough capacity in the network to meet our SLAs? We want to be warned if we're approaching that point, or have something flashing red if we're exceeding our available capacities. Here's a concept of taking that same information and presenting it in a more sort of classical way in dashboard form. We talked about the different sources of truth. SNMP is great. We can also pull from things like NetFlow, streaming telemetry, and so forth to be able to account for sort of exotic types of links like IP over avian carrier, IPv6 over social networks. This is a screenshot of the mock-up we did of that dashboard. If you squint, you see in the upper right-hand corner the path capacity is that grid I talked about. And we can color those according to how close they are to our target thresholds, sort of green, yellow, red. And in a sort of the stretch goal we had was to be able to sort of paint on top of the topology the instantaneous or the recent capacities for each of those links. And so after some time passes, those path capacities get updated. And in the lower right, this is sort of the underlying data showing that for a maximum flow end-to-end between two endpoints, in one direction, how much of each of the links is used to provide that total end-to-end capacity. And then I'm going to quickly just show a demo of that should be working. So, if I reload this page, I'm seeing that the path capacity from host 1 to host 3, the end-to-end path capacity is only 5. I'm using capacity of 10 embedded in the network, and we're getting 5. And then after a few seconds on the back end, we're sort of using that fake data to generate new conditions. So if I reload, I should get an updated set showing new capacities. So this is more of a sort of a nominal condition where I have greater capacities from the endpoints. Did I miss anything? Okay, that's it. Thanks.
Awesome, thank you. So next we have the injectors. The injectors. After the injectors, we have streamers. So please be ready.
Okay, so we are the injectors team. So we are our team from Clarkson, from GCT, Nokia, and Facebook. Our objective of this project is about network automation. So basically, we want to automatically check some applications. Here we are using HTTP, but actually any other applications we could check, and we are able to dynamically add routes, withdraw routes based on the status we checked from the application layer. So so the basic idea is that on this host who organize all these applications, we are announcing BGP routes to the network, right? So then we have all this reachability, for example, in a data center environment. And on the host, we have 3 modules. So we have the server and the BGP injector and the BGP server. Here we are using Go BGP. So the first step here is actually we done all this together. So we implement 3 modules, and also we configured the connection between the BGP server and the Tor part. So from the web server perspective, basically we customize our own HTTP server, and we are able to generate some random status code, and we are able to log like the request IP from which user, and the SURL, and the response status code. So the next step is the injector. So we are able to regular check HTTP status, for example, every 5 seconds, every 2 seconds. So we are able to basically, actually, as our future work, we want to make this more flexible. So right now we are using every 5 seconds. So we check the web server status. For example, if it returns 200, we will insert a route to the BGP server. Otherwise, we will withdraw it. Basically, tell the network, so this web service is not available. Go to other web servers to get the content. So and also we have this BGP server. So it's responsible for talking with the injector using Go RPC API, and also we announce BGP routes to the Tor. And the Tor, actually, we also advertise all the routes from the injector to the whole network. And we are able to basically tell the network, the service is available at this time. You can go ahead to retrieve your content here, and otherwise, go other places. So, so right now, probably Victor, we can help with them.
Hey everyone. So right here in the top left, we have VMX7. And it's showing us the responses from each host. Right here, we have one of the leaf nodes. You can tell what is connected, what not. Oh, topology. Of course, you guys have all seen this. But VMX7 up here, then we have leaf 2 and host 2, and those are what I'll be showing you all. So right here, we're getting hello from host 2. Seems to prefer host 2. We haven't really figured out why. Something with the boxes. But down here, we have a randomized code, so you'll get a status 500 about 10% of the time. And you'll see that in the leaf node. And if we disconnect, you'll see a drop in contact from host 2. It was working 5 minutes ago, I swear. Yeah, this connection. That works. Yeah. And yeah, I don't think it's it kind of died. Yeah. It was working a few minutes ago. But overall approach is exactly. Yeah. Yeah. Thanks, everyone. Thank you.
All right, so next we have the streamers. And after that, we will have Go Jet Yourself.
How do we present? What's the do you have an adapter? No, like a USB-C to
Does anyone in the room have a USB-C to HDMI adapter? Anyone? Oh, thank you very much.
We saw everyone had a presentation and we thought we probably should do that. There you go.
There we go. So we're team streamers. We don't have a PowerPoint, so instead Tom just wrote something in Notepad 3 minutes ago. So we were working on something fairly small, more closer to the demo from last night. The basic idea was managing egress load balancing. So if we have certain links that are burning down on egress, the goal was to inject a BGP, more specific BGP prefix, and shift traffic over to a different egress. We did end up getting rat-holed a bit, so we got the traffic generation working with iPerf from the rack switches, oddly enough, and we were looking to use NetFlow. We went on a bit of an adventure there. After much trial and error, turns out the VMXs cannot stream NetFlow over the FXP interfaces. However, they can stream in-band down to a host that has a UDP proxy that flips it over to the management network and streams it back up to the jump host. So after much trial and error and consternation, that we did not end up using NetFlow. Instead, Tom just pulled the interface stats using netconf, which was a much better idea. However, Tom was much more successful in getting some basic traffic shifting actually working. So Tom, if you'd like to explain that and show the demo.
Certainly. So we converted the network to code topology into different. We made the VMX7 basically like a transit router, like an ISP router, and then 8 and 9 were our edge routers, which weren't connected together for some reason. Basically, this is demo vision time. That's the second slide. So basically, sorry. Okay, so the prefix that we're using for traffic was 20/8, and as you can see here, that just goes up there. So in the code, we use the GoBGPD service, and we fire up a router. We connect to both of our edge routers. You'll see the second one come up in a second. Then we pull the stats. So it's pulling the interface stats. That's kind of the interface name, inbound, outbound, bits per second. It's grabbing the second edge router's upstream interface now. And you can see that second one there, VMX9, its upstream interface is doing a lot more traffic. So it's now moving .3 over to the other router. If we look at the routing table, you'll see there that the prefix is there. And just ignore the fact that they're both going to the same next hop. That's just a little little bug that needs to be fixed. But yeah, I mean that's kind of working. So yep, done. Done up the shooting time. Thank you.
I think that's it.
All right, thanks. So next up we have Go Jet Yourself, and after that will be the Downtimers. Everybody's favorite group.
Also use the USB-C to HDMI adapter. Thank you. Which way I should plug into?
Things like.
Okay, so we tried to do similar based from some discussion too, looking a bit about the like performance for the egress. The idea was like we have a web server, we want to figure out basically change it around the outgoing traffic based on different metrics. We had the ideas to look at ICMP latency parts, so like ping times for like what's coming in. We looked also about can we do like interface performance there if that's where that chat thingy comes from, and the answer is no, we cannot. It seems to be, I'm not sure you want to give details what that failed or. Yeah. So that part didn't work out, but we got the rest of it basic up. So what we have is, let's go down to this network topology first. We have here this fancy network topology. And as you may not be able to see is we moved one of the host 1 up to the top. So we have like on the very top, we have a web server connected to the top VMX, and we have multiple hosts below. When these hosts connect to the web server, we look at the IP address. We do then, while we serve also the page, we do a ping check there. We look at the latency. We see like which route works best. Is it like rather going to VMX 8 or 9, which one works better? And we then go and update the routing table based on that. We obviously also worried that BGP sessions may go down and change again. So we also use BMP to monitor the BGP sessions on the DMX 789. So if some of these BGP sessions go down, we basically go and remove the routes again. So if like the DMX 8, which is the one on the far left, if any peers go down, we basically remove all the routes which we inserted towards that router, which then will be learned again afterwards. And yeah, I think that's it. Let's do some demo.
Yeah, I'll show you guys a short demo. One sec. Okay, so here we have our current routing table. This is just. Yep, sorry. So now we have our current routing table. As you can see, this basically has the routes that were provided on this host initially. So we have our little server running here. So this is a web server, which is also doing the ICMP testing and the other components. So I'm going to go over here and basically just hit the web server from a couple machines. And so you'll see over in this window here, we're actually going and looking at these hosts that are hitting the web server. We're actually running ICMP tests down multiple transit paths and then determining over here which is the best route for that host. So if we go back over here and look at the routing table again, you can see that we've now injected these 3 entries here. So now if I go back over here and, in a sec, my window is a little too big. Now if we clear one of these neighbors here, and go over here, you can see withdraw VMX 8 because the peer went down and this route was deleted. And you can see that it disappeared from the routing table over there. We can do the same thing with our other peer. Sometimes takes a few seconds.
We noticed that BMT is sometimes extremely delayed for like 10, 15 seconds. We haven't really figured out if that's configurable. I'm not sure if anyone here knows what the reason is.
Yeah, it seems like you can't set it below 15 for whatever reason.
So, yeah. What you see there too on the withdraw before it says now it claims withdraw VMX9. So.
Yep. And now we're back to the original routing table.
Yeah, basically.
Cool. Thanks, guys.
All right, so now we have the down timers, and after that will be every day I'm Poland.
All right, cool. Is this thing on? All right, it's cool. Hi, I'm Colin McIntosh.
Aaron ATAC.
So a little bit of background. So we are maintenance traffic controller. So this is about shifting traffic based on planned maintenance notifications. So a little bit of background. Everyone gets too many maintenance notifications. It's too hard to track them all. And if you have a lot of circuits or connections or peers, it can be a pain to manage maintenance around other people's planned downtimes, putting things into maintenance, taking circuits down, moving traffic, things like that. So with that, our project is
to read partner maintenance notification emails, which is already done. This was worked on at the last NANOG Hackathon, and then shift traffic off network links during the planned maintenance. So the way that we're doing this is using identified circuit IDs to match with device and peering sessions. Create a schedule of peer sessions that need to be turned up and down, and create a daemon that watches the schedule and shifts traffic before and after maintenance.
So how it works, as you can see up there, we have the first part of it is getting the email from partners and parsing out the maintenance details. That's that managed maintenance project, which is the previous one that we worked on. What we worked on this time is building the schedule of maintenance events, that maintenance traffic controller you can see there, and then actually interacting with the device and shifting traffic. So the main part that we worked on this time was the controller. So this really just watches the schedule for changes. and it looks for events that are coming up with a near start time. I think we set it to 5 minutes. So if a planned maintenance event comes up in the schedule, within 5 minutes, we will go and execute whatever config we have to go shift traffic off of the circuit that will be going down, or the peering session, or whatever it might be. And then after the maintenance is done, we have a feature that will disengage the maintenance mode, bringing traffic back onto the link.
Okay, so it can be very flexible, and there are many options for moving traffic. Currently, we're using Jinja 2 templates to create command scripts. This is just an example of using deny any or AS prepend to shift traffic. The idea is that if you hypothetically want to keep the session up but don't want to receive anything from or going to the BGP peer, you can just put a deny any on the import and export or in and out. And then if hypothetically you don't want to completely block off the traffic from that peer and you want to keep it up, but basically shift the traffic, then you can set the local preference on the inbound policy to a very low local pref, and then AS prepend out, so that it would always prefer a different route with a shorter AS path. But at the same time, if hypothetically that other route that you had or other peer that you had was experiencing issues as well, you may not necessarily want to completely cut your peer that is in maintenance off. So you can still use them, but at a very low priority.
And the other thing to mention about this is that because it's using Jinja 2 templates and just executing some basic commands, it would be very simple to implement your own version of traffic shifting, however it applies on your network. So here's a little example of a demo. We're not actually going to run the demo because it doesn't really do much aside from sit in a loop and check events. So here we loaded in basically a fake maintenance event that was coming up in a couple minutes. We started the scheduler. It watched. It saw that there was an event starting soon, and then it kicked off our Jinja template on the switch, logged in, ran the commands to shift traffic, and here you can't see it shifting the traffic back, but eventually it would do that.
So the future work is to check up the link and BGP status before restoring traffic to the link, support more routing protocols than BGP, and enable maintenance mode and an alerting system, an example like Nagios to suppress alerts.
So just some other things. Other people have mentioned, ISIS or OSPF, or however you're managing traffic on your network. There's plenty of other options for moving things around. But yeah, there's a link to the code. The code's already up on GitHub. It is functional. If you want to go try it, it's very static right now for this. But yeah, that's all we got.
All right, so next we have Everyday in Poland, and after that we'll have flow symmetry.
Hi, so we actually don't have any slides. A few of us are really new at coding, but I think the idea was that we were going to carve up the two data centers, DCA and B, so that they're separated by some transit provider, but also have some sort of metro link between them as well. And the idea was that we were going to use SNMP and put the data into InfluxDB to get an idea of the levels of traffic. From there, we were going to potentially look at NetFlow to figure out if we could take certain host routes, say host 1 to host 3, and then inject dedicated routes to reroute the traffic over the less preferred transit link. So we explored and got data, and mostly Jade got data into InfluxDB. We got open BMP working, but we just never got to a point where we could actually get something usable, although we were getting there. So that's it.
All right, and flow symmetry.
Where's our V12, my favorite animation in the world. Hi, we're the Flow Symmetry team. This is Vasily, Malachi, Adam, and I'm Chris. We identified a problem statement of asymmetric data flows. BGP by default will hot potato traffic outside your network, which is great for which is great for ISPs that want to keep their costs down. Content providers, gaming companies, not so much because they want to control as much of the path as possible. The illustration of a asymmetric flow, the problem becomes that you don't have much control over that path once the packet leaves your network. So a solution we devised involved watching NetFlow data to see the incoming flows, compare the source IPs and the incoming interfaces to the routing table to find out if the return path is the same as if the egress path is the same as the ingress path or not, and if it's different, inject the route to override, thus creating a nice symmetric flow with a predictable path in both directions. The components we used, a flow analyzer tool, open source from Magneto Networks, Kibana for Elasticsearch to pull out flow data, and the good old GoBGPD and BGP control that Brandon presented last night. We got all the pieces working individually, didn't get quite to the point of an integrated solution, but here are the pieces. We got NetFlow export, logging, and flow reporting up and running. We wrote a route injector that could both add and delete BGP routes. The work to be done is taking these two pieces and gluing them together. Your tried and true command line API should be replaced by a JSON or RPC. That's it.
All right, so James and I are actually, a final group. James is, going to attempt to plug in his laptop. I'll do mine first. He has Linux, so it might not work. So our group name is Go Fail Hard. I hope that doesn't give away too much about our project. So we don't really, we kind of had a small plan. The idea was just let's inject some routes. This is all going to be way too small, I'm guessing. Let's inject some routes into a table, into a local BGPD controller. We're going to read how many we have in there. We're going to write that into an InfluxDB, and we're going to display that. And we're also going to stream BMP data over to this laptop. We're going to process that BMP data and put that into some sort of structured format in InfluxDB as well. So here, there's not much to see other than that 10 will turn into a 0 periodically. I just kind of have a very simple loop that sits around injecting 10 prefixes and then deleting those 10 prefixes. So yay, learned how to write Go. That was exciting. And now James will show us the other piece.
You need one?
And we're going to need another dongle, it seems. Oh, I didn't realize you could do dongle.
Yeah. There's zero chance of this working, but it's worth a shot, hey. So anyway, yeah. So the idea was to basically stealing the idea of Brandon's BMP collector that was sort of his collector anyway. Seeing how much metadata we could actually get out and make something useful. Yeah, that's not going to work. Anyway, so the idea was to basically pull out the metadata. So things like I got really kind of bogged down in trying to get the BGP update stuff out of there, but like essentially trying to get more metadata because I find it really useful for the BGP data to actually have things like updates, withdrawals, everything else in like a database who was using Influx, and then we can kind of follow along like kind of like any, you know, I think what is it? Not BGP one. Is it BGP one? The external service that does this? Like you can do BGP graph, that sort of stuff, but have an internal version because obviously inside your network you don't have that sort of visibility a lot of the time. I wish I had could show you something, but anyway, he's streaming BMP data to me. I'm throwing it in FluxDB. Cheers.
And surprisingly, it didn't crash. All right, so that's going to be it for at least what we're live streaming, so we can probably finish it off now.